Okay, thank you, and good afternoon, everyone. So first of all, thank you all for those excellent talks. And today I'm going to talk about, how high energy physics experiment DUNE is using HDF5 as raw data storage, and also using it as different stages of its data processing chain. So before I jump there, let me introduce DUNE a little bit. So DUNE is a long baseline neutrino oscillation experiment, and it is also a multi-decade and multi-billion-dollar experiment. It is also a leadership experiment in neutrino physics from the United States. And DUNE is supposed to start taking data in 2029. So DUNE primarily consists of three major components. One is Near detector, which is located at Fermilab, which will be built at Fermilab, and a far detector, which is about a mile underground in Sanford Underground Research Facility, and an intense neutrino beam that will run from Near detector to the far detector. Now, a far detector here will have 4 10-kiloton liquid argon TPC modules, and we are going to follow two different technology. One is horizontal drift technology, the other one is vertical drift technology, and we call it HD and 3D. Okay, so this is actually one of those 4 far detector modules. Okay, so DUNE is currently prototyping 2 detectors. One is ProtoDUNE HD and the other one is ProtoDUNE VD. And both the detectors are currently sitting at CERN neutrino platform in Geneva, Switzerland. These are some interior views of our prototypes. Okay, this is just an overview of our ProtoDUNE HD detector. This is our detector sitting at CERN. See that we have got 2 anode planes. One anode plane is right on this side, the other plane is on the back side. Right here in the middle is the cathode plane. So the charges are flowing from this cathode plane to the anode plane. Now, an anode plane has 2 APAs. APA stands for anode plane assembly. So for this detector, we've got a total of 4 APAs. And we can imagine an APA as the structural or as the computing unit of the entire detector. And this is a quick overview of the operating principles. So if this is the detector, which is filled with liquid argon, the neutrino beam interacts with the liquid argon, producing ionization electron. The electron moves horizontally, gets captured by these 3 planes right here, and then the signal gets spread out by our data acquisition system. We call it DAQ. Okay, so this detector is currently taking beam data sitting at CERN. And this is our ProtoDUNE VD. This was all about ProtoDUNE HD in earlier slides. This is VD. Everything is pretty much same, and I don't know why it is not showing the full slide. Okay, so this is the VD. So the operating principle and the detector technology are pretty much same, except that we have 2 anode planes here, one at the top, one at the bottom. Cathode is in the middle. The electron here are moving upward and downward. And this detector is scheduled to take data, in 2025. Okay, so this is our DUNE raw data volume. As I mentioned that we are currently taking data for ProtoDUNE HD, and we are reading only 4 APAs here. The detector readout time is 3 milliseconds. This is also what we call one event or one trigger record. Now, the uncompressed raw data for an entire event is 120 megabyte in size for the ProtoDUNE HD. So we've been taking data for probably the last 5 weeks. So by this time, we have gathered, I think, 1 petabyte of raw data. Now, based on ProtoDUNE HD, we can also predict the far detector raw data volume. For the vertical drift, we are going to take 16 petabyte of raw data per year. And for the HD, we are going to take 9.4 petabyte of raw data per year. So remember that these are only 2 modules of the far detector. There are additional 2 modules for the far detector, and also DUNE has got a near detector. So it's a substantial amount of raw data that DUNE is going to produce. And all this raw data is going to be written in HDF5 format. Okay, so for both prototypes, we are actually following the same offline data processing strategy. We start off with DAQ. DAQ reads data from the detector and then writes it out in the HDF5 format in local buffer at CERN. And from CERN, all the files get transferred to different locations, for example, US, UK, India, and many more. Okay, so by the time we receive the files in Fermilab, the raw files are also in the HDF5. So after that, we start actually the offline processing, for example, signal processing, hit reconstruction, pattern recognition, etc. And this section that you see for offline processing is a mix of root and HDF5. Now, finally, introduce some analysis sample. This analysis sample is basically high-level physics format. It is currently in root, but there is a potential use case of HDF5 in future. All right, so here is our how we represent data. Our DAQ data acquisition system decided to explore HDF5 as for storing raw data. And we have successfully taken data in ProtoDUNE HD, particle drift cold box testing, and one of the detector prototypes. So it is a successful venture. Now, that being said, DUNE will not only support HDF5, it's also going to support a different representation of data, for example, root, JSON, binary, etc., etc. And we also need compression for raw data, HDF5 raw data. For ProtoDUNE HD, we have not used any compression, but for the FAR detector, the data volume is substantially large. So we're going to apply some compression factor. And for that, we are working with HEP-CCE group to explore different compression and what compression we can use for different data set. Okay, so here is how we write the raw data by our DUNE DAC. We use HDF5 libs. This is actually the library for writing and reading files in DAQ software stack. This repository basically contains the classes that are used for interfacing between DUNE DAC data applications, for example, readers and writers, and the Hi5 library to read and write HDF5 file. So there are two major classes in use, HDF5 file layout. This is actually taking care of the DUNE DAC raw data files. And there's another one, HDF5 raw data file, which is the main interface for writing and reading HDF5 files. So for this one, we can handle one file at a time. So if you're trying to write multiple files at a time, you have to create multiple instances of it. Now, we also write it in such a way that, later on, the file can be interrogated with any HDF5 reading utilities. Okay, so here are some key principles in terms of writing data fragments into HDF5 format. We write the data from, the data sets should have the granularity that is meaningful and manageable for offline data processing. The second point is data must be self-describing, which is the file should know what is in them, and also it should know all the information, about how to navigate through the files. And also tools for reading and reading data must be backward compatible, which means how the files and data are organized must be versioned. Okay, so here are some key features of our data format. Those are data sets, groups, and attributes. So DAQ data fragments are being written as data set, and all the data fragments are grouped in a reasonably organized ways to reflect the physics needs or to reflect some organization in the file. And then there are some attributes which can be attached to different stages of the data set. And this is something we call also metadata. So each data in an HDF5 file is recognized by 4 identifiers: run number, sub-run number, trigger record, and sequence ID. And the size of the data fragments are determined by the block of data that we can efficiently transfer within the DAQ. Okay, so this is a generic structure of how data is organized in a file. So we have a root group, and under that root group, we have file level attributes. Within that, we have the trigger record. This is a group called trigger record, and this trigger record corresponds to one trigger decision. Trigger record consists of trigger record header and a set of fragments right here. So each fragment here corresponds to a part of the detector and consists of a fragment header and fragment payload. The fragment payload is actually the raw data that is coming from the detector electronics. So every single fragment here actually containing real data, raw data. Okay, so once we have, once we write the data, next is reading out HDF5, using our offline event processing framework called ART. Now, ART is pretty famous in the neutrino experiment, and it is basically done in the Fermilab. Most DUNE ART jobs use ART root files as an input, and ART's root input source is quite well featured. It has pretty much everything we need. So to integrate HDF5 offline with ART, we needed all those functionalities similar to root. So we implemented these 3 points, delayed reading, input source, and decoder tools. So input source is just opening and closing the file and leaves the file handle in the ART event memory. And decoder tools is really one which is doing actual I/O and deserializing the data. So we have shared input sources for all the detectors and also the individual decoder tools for every single prototype. Okay, so we also need to stream HDF5 with XRootD. There are multiple reasons why we need to do that, but of those 2 are most important because HPC tools need to transfer HDF5 files within an HPC site, and we also need to do a quick analysis, to check different parameters, physics parameters, when data is generated. So for the time being, for the time being, the solution was streaming with XRootD using dynamic library, which is actually using the LD preload to load the XRootD POSIX IO. But this is not a robust solution, and to make it robust, we think that we need to link HDF5 with XRootD through the static library. To use the static library with HDF5, maybe we need a static virtual file layer interface between HDF5 and XRootD. So this work is in progress. Okay, so data from Supernova neutrino burst will be collected in the FAR detector, and data set is significantly large for Supernova, pretty much 180 terabytes per event. So this is pretty large data. It is highly challenging to process all of the 180 terabytes in one go. So we may want to read parts and pieces and regions of interest, what we want to process. So this is where we really need the hyperslab selection. So a selection and multiple selections in Supernova data space is currently under investigation. And we all know that those sort of selections work best when data comes in uniform blocks. So we are also thinking about how to collect data or how to write data in DAQ for Supernova. Okay, so this is our current ProtoDUNE model in HDF5. So we start off with DAQ output HDF5. We go through ART or LARSOC. This is the standard event processing framework. We produce ART root file, and then we apply root to process to produce CAF. And CAF is actually some conventional entable just to do some physics analysis. So that's our current one. And this is our potential ProtoDUNE data model. And this we may want to deploy this model in our FAR detector. So here we start with DAQ output HDF5 format, and this go through HPC and GPU for running these algorithms: signal preparation, Gaussian heat founder, heat disambiguation, etc., because these are the processes that need GPU. And then again, the output of these processes would be HDF5 file, but it is going to be a GPU friendly format. Now, for this row, we are trying to make the optimized HDF5 format for GPU. And for this section, we are working on HEP-CCE group to find out the optimized data. Now, the advantage of doing it this way is once we have HDF5 here as an output and in a GPU-friendly format, we can directly feed it into the existing machine learning or Pandora algorithm for full event reconstruction and classification for DUNE, or you can actually go through the traditional way, going through the large soft art and follow the traditional reconstruction chain. Okay, so in summary, I think that DUNE has made good progress on using HDF5 online and offline, and we've been able to read and write all data produced by DAQ. Streaming with XRootD works, but could be made more robust. And in future, we are collaborating with HEP-CCE for GPU-friendly format. We are also trying to simulate neutrino event generator and giant into HDF5. We're working on parallel IO, et cetera, and we are sort of envisioning collaborating with HEP-CCE on HDF5 streaming. And here we are, DUNE collaboration. We are more than 1,400 collaborators. It's no longer 1,300, it's actually 1,400 collaborators from more than 200 institutions and 30 countries. Thank you very much for listening.
Do we have any questions?
We got into the streaming API side of the world this morning. How well do you feel that will meet your needs?
The streaming one?
Yes.
Okay. So let's put it this way. Right now, we are taking data in ProtoDUNE HD, and we have a sort of a way to do it through the dynamic library. But in future, for PAR detector, yes, we definitely need the streaming. But if you're talking about it right now, no. But yes, definitely for the PAR detector, we need that.
With that API, I mean, he was pushing back a little bit about no more API, right? But I'm simplifying it down to just, set up, right, stream right, stream event, then close. Adding in some custom APIs is good, bad, don't care.
Okay, for now we are using C API because we have some trouble using C++ API.
Yeah.
So yeah, C API called from C++. That's all you're using. Now there's a catch here because what I was talking about is the PAR detector. For the Near detector, they are also using HDF5 API, and they're all using Python. Now, what they're using there as API, I'm not quite sure of right now. So I would say we don't care as much as we can work it with. In our existing framework, of course.
Sure. Okay. Cool.
Anyone else? Thank you so much.
Thank you.